Recording. I think we are live now. Yeah. Come on, load. All right, I think we're live now. Let's switch over. Alrighty, let's get started. So, the very first problem that someone shared with me was, where was it? Find a parametrization for the intersection of the paraboloid, which is just z is equal to 9x squared. By the way, can you see my screen? For the people on Discord, can you see my screen?
Yeah, I see it.
Good. Okay. So for problems like these, the idea is these two surfaces are a little bit tough to imagine, but like hopefully not too crazy. So a paraboloid is just going to look like, I don't know, how do you want to draw this? Something like that, where it's sort of a, not necessarily a circle, but kind of like in a, each cross section is kind of an ellipse. And the parabolic cylinder is, so that's the top equation, and the bottom equation is, I don't actually even know what that is. I think it's basically like y is equal to 4x squared. It doesn't really matter because they don't actually ask you to draw it out. But for the sake of just concreteness, I like to think about what this actually looks like. So if this is x and this is y and that's z, if we just pretend that the z-axis doesn't exist for a second, this just turns into a parabola, right? This is just a genuine parabola from 8th grade algebra. And then if you add in the z-axis, it's basically like saying the z here is just totally unconstrained, which means that it's sort of like the z, the x and the y is sort of like the base, but the z can be any height it wants. So it sort of turns into this like, it's very hard to draw, but it's kind of like this curved piece of paper. Can you kind of see that? And it goes both up to positive infinity for z and both down to negative infinity for z. Is that reasonably easy to see? Or?
Yeah, I understand.
Okay, so far so good, I suppose. By the way, just for people joining us, just be aware that I'm recording, or rather streaming to a unlisted video, which I will later share for people who missed it. But what are we looking at right now? The question I think for us was, okay, so we basically visualized what's going on here, and the intersection of the two is just kind of even more awkward to picture. I don't even know how to describe the shape, but like you can imagine that they can intersect, right? And what it's asking you to do is take the setting x is equal to t and using the two equations to write y and z in terms of t. So this seems really complicated at first, but the bottom line is that what we want to find at the end of your answer for this problem is like WTF. Means that we're going to want an expression of x in terms of t, we want an expression of y in terms of t, and we want an expression z in terms of t. That's what we're searching for here, right? The I guess this is the equation, the expression involving the, sorry, I guess this equation expresses the surface or the line of intersection. But the idea here is that they already gave you x of t, so which is just t itself. So okay, let's call that t. And the idea is for y, all right, let's just plug in t. You could basically use either of the equations, but because this one is y in terms of x without even mentioning anything about z, this one sort of gives us the more direct information relating x to y. So plugging that in, we get y is equal to 4t squared, right? And the last piece of this problem is essentially asking us to solve for z as well. At this point, we know that x is just t squared, so this is 9t squared, and y squared is, y is 4t squared itself, so that sort of turns into, what is that, like 16t to the fourth times 2? The idea here is we just keep plugging things in. We already know x in terms of t, we know y in terms of t, so just plug everything in and get z in terms of t as well. And I'll leave the rest of the problem to you, but you should be able to come up with an expression all in terms of t right here. Just figure out what this is. Is it clear what it's asking you to do? Like, it's kind of hard to visualize what exactly is happening just from this equation. Like, I can't just visualize what's happening when you have t 4t squared and like some crazy t to the fourth term here. But in terms of the nuts and bolts of calculating this out, it should be reasonably straightforward, I hope. Seem okay?
Yeah.
Okay. So then the second part is essentially asking you to start by setting x equal to a different function of t. Yeah, so use the equations to write y and z in terms of t. Does the resulting parametrization give you the entire intersection or only a portion? So the idea here is that, how should I put it? Remember, we kind of glossed over this at the start, but the idea is that they sort of just chose x is equal to t right from the get-go. Yeah, just basically immediately. They could have chose something else. They could have chose x is equal to cosine of t, or maybe t squared, or some crazy thing or other. And what the problem part B is asking you to do is just, okay, go ahead and choose something else. Choose a different function of t. I don't know, maybe square root of t, or t squared, or cosine of t. Some of them are going to be harder to visualize or work with than others. I mean, I would already say that just setting x equals t is already hard enough to visualize. But what that's basically saying is, between the paraboloid and the, I guess they call it a parabolic cylinder, it's sort of like saying x can take on any value, presumably between negative infinity and positive infinity. And then the intersection will just try to figure out, by using this expression, it'll just try to figure out where the two intersect. But the idea is, if I chose something like t squared, right, and went through the exact same process again of letting, this time maybe x is equal to t squared, y is equal to, I guess, 4t to the fourth probably, and z is equal to whatever it is, I'll let you figure it out, or use your own parametrization, maybe t cubed or something. The idea of the question is asking is, does the resulting parametrization give you the entire intersection or only a portion? And this is where you start having to use your brain a little bit, right? But the idea here is, whereas this one could let you go from t from negative infinity to positive infinity, I think, t squared is only going to be positive, right? T squared is only going to let you go from 0 to positive infinity. And what that means is, if you look at this, maybe if you look at these, this parabolic cylinder, the paraboloid and the parabolic cylinder, what this means is that sort of only if I use the t squared parametrization, I think only the positive parts are going to be remotely, are going to be mappable, right? There might be more constraints, but that's sort of what it's asking you to do. It's sort of like saying, whatever you choose, right, try to think about it a little bit and see if whatever you get still can like span the entire intersection. You kind of see what I mean? It's kind of a hard concept, and they're not asking you to be very rigorous about it. They're just sort of trying to ask you to kind of visualize it and describe it verbally. But do you see what's happening here? Do you see how choosing t squared restricts you a little bit? At least for the x? Yeah. Like the y and the z, I don't know if they get restricted that much, because like y was going to be positive anyways, and z was also going to be positive anyways, because they comprise only of squared terms. But the original x is equal to t could have taken on negative values. But now using x is equal to t squared, now it can't, so you're kind of constraining it to a portion, right? And the same is going to be true if you chose x is equal to t to the fourth, or maybe t to the sixth, or any even power, really. But off the top of my head, if you chose an odd power like x is equal to t cubed, or a t to the fifth, I think it's possible that those values will span everything. Because like t cubed will go from, like x is equal to t cubed, will go from negative infinity to positive infinity. And just off the top of my head, I think that hits everything. And what I mean by hit everything is, like, literally, will a certain point on the intersection be achieved? Or will it be missed out on because our parametrization was kind of limited? That's what you got to think about. For this problem, I would probably advise away against something like hard to think about, like cosine of t, or actually square root of t might be okay. Nah, that one's going to be hard too, because then, it's taken to be the positive square root, so you're also sort of throwing out the positive values. Oh, sorry, it's throwing out the negative values, but this is sort of what it's asking you to do. And I hope that makes sense. A lot of these problems are not so computation-based, they're sort of visualization questions. And that's sort of a big part of early multivariable calculus, is just getting you to visualize the right thing. But sound good so far? Are we on the right page?
Yeah.
Okay.
So
Alrighty.
far, so good.
What's up? Someone else say something? By the way, just for the new people joining
I was
us.
saying things sound pretty good.
Okay, for the new people joining us, I'm also recording, and technically I'm streaming to an unlisted thing, but I will make it available, make the link available for anyone who misses it afterwards. Anyways, so question one, I spent a lot of time on discussing just because I think it's good to get a foundation. But the next three are all kind of similar. They're just slightly different, slightly harder versions of each other. But we're asked to visualize the intersection of, I think it's just saying a cylinder intersecting a plane. And it could be like, I think it could be any plane. They're not necessarily asking you for that particular one. But okay, so this is like an infinite cylinder. So x, y, and z, it's sort of saying that the radius of for x and the radius of y, or rather, sorry, it's saying that the radius is going to be 3, right? Because the r is just equal to 9, 9 is equal to r squared. But again, what's happening here is that z is unconstrained. So z can basically go, as high as you want, or, as low as you want. And maybe the way to start thinking about these problems is just to think about what this looks like in 2D. That's just going to be a circle at 0, 0 with radius 3. And then maybe think about the z afterwards. It's sort of like beaming it up to infinity and beaming it down to infinity. It's kind of like the opposite of a projection. This only works for like relatively simple problems where one of the equations can be thought of in 2D first. But okay, now it's asking you to draw it intersecting with a plane, right? Intersecting with a plane. And I'll just draw something really simple right now. What if it just intercepts like this, and it's totally, let's say that this is totally parallel to the XY plane. Heck, let's say that this just straight up the XY plane. Can anyone just say to me what shape this is going to be? I mean, I'm drawing it, but like, can someone say it out loud? I realize that seems pedantic, but I'll get to the point in a second. But literally, what shape did I just draw here? If this cylinder is intersected by the XY plane.
Like a circle with, yeah, a circle, right?
Yeah, exactly. A circle with radius 3. And
2D circle.
yeah, I guess that's a reasonable clarification, but yeah, it's a 2D circle, right? I just took the slice. Remember earlier how we said I kind of start with the base, which is just a circle? Well, by taking the slice by intersecting with a plane, I've basically just gone right back to that 2D circle we started with. But the reason I do this is basically to say, okay, let's test your visualization skills. Now what if I like kind of tilt this plane up a little bit, right? So it's no longer a perfect circle, but it does still kind of like go all the way around and touch itself, right? Any idea what this shape is going to be? You don't have to prove it to me, but just intuitively, what is this going to be? What is a distorted circle called?
Ellipse?
Yeah, I think that's a pretty reasonable guess. I think that's what it is. I haven't proved it myself, but it seems like a very reasonable thing. Yeah, so, I think that's really all it's asking you to do is just draw it out, visualize it a bit. But, go ahead and draw your own pictures. What else is relevant? They did tell you, because part A doesn't specify which plane, you could also just imagine kind of like cutting through with a plane like this, right? And what would happen here is it wouldn't hit anything on the top. It would just hit like the sides, right? So intersecting with like a vertical plane like this would just give you 2 lines. I think that's a reasonable corner case just to bring up. But I think the spirit of the problem is asking you about the circle or the ellipse instead. And whether it's a circle or ellipse depends on whether or not it's perfectly at the right angle or not. So, okay. Next part is saying in the plane, equation x squared plus y squared is equal to 9. Describes a circle, find a parametrization. At this point, I hope from your pre-calculus days, this should hopefully come just by heart. But this is, x is usually equal to r cosine t, and y is equal to r sine t. And you should be able to figure out r right away because that's the radius of the circle. And you can get that just from looking at the other side, which is just r squared. Right? So yeah, 2D parameterization is not so crazy. But now it asks you to say, okay, so this is our 2D parameterization. We have both x and y. Now let's solve x plus 2y. You know what? I'm gonna make up my own. Equation. I don't know, 3x plus 5y minus 2z is equal to 10, maybe. And the idea here is that you can just totally isolate this for z, right? This turns into 3x plus 5y minus 10 is equal to z, and just divide that by 2 to isolate the z. But the idea here is you have this expression for z, and it's like, oh man, this is kind of a little nasty, right? But just like at this level of math, sometimes even if things are uncomfortable, you kind of just got to charge ahead and go with the calculation and maybe try to visualize it or do a sanity check afterwards, right? Some things like this, when I'm going to go ahead and plug this in, and keep in mind that at this point, you should have found an explicit number for r. But yeah, you go ahead and just plug these values in. And this gives you z in terms of t, right? It's kind of unclear what this like visually means, because z is going to be written in terms of a combination of cosine t and sine t, but you can get the answer anyhow, right? In terms of actual computation, this shouldn't be so bad. Agreed? Or are there any questions right now? Right? Like this term right here looks a little mysterious, but I'm sort of asking you to take a bit of a leap of, not quite faith, but maybe a leap of confidence and just go ahead. What questions do you have at the moment?
Would you put 3 cosine and then plus 5 sine t?
Almost. You would have to just figure out, also account for whatever your r value is, right? Whatever your radius is.
Oh, yes.
Yeah, but I mean, saying you've already got your x in terms of t and your y in terms of t. Literally just take those and plug them in, and that's your answer for z. That's all I'm saying. Make sense? So for part D, at this point, so maybe I'll write it out a tiny bit more explicitly, but this is basically x in terms of t, and this is y in terms of t. And all the next part is asking you to do is just literally just take your answers from parts B and C and just write them out with a tiny little bit of notation. Right? You can either use the angle bracket notation, or if you like, you could use the I hat, J hat notation. Whatever floats your boat. But it's literally just asking you to write things in terms of some sort of vector notation. Yeah, and you'd probably call this like, I don't know, maybe P of t for position or something like that. But the point is, this is what they're looking for. Right? The vector parametrization of the intersection. And you understand why this is a parametrization, right? Like t is the parameter right here. What this entire problem is asking you to do is literally write everything in terms of an arbitrary t. And it's sort of like saying, whereas before you had like, maybe let's motivate it this way. At the very start, you had this two equations, x squared plus y squared is equal to 9, and also whatever crazy plane equation you had. And like, it's kind of unclear what the relationship between these variables are, because they're not totally independent of each other, right? Once you set x, some constraints pop up for y. And then once you set x and y, some constraints pop up for z. The spirit behind this problem is sort of like untethering them a little bit and putting them all in terms of some new independent variable t. Does that make sense? Like, parametrization is definitely something you've done before at high school or lower level math, but I think that they tend to do a pretty bad job of motivating why you do parameters. I know that when I was a high school student, I was like, man, I hate this. What's the point? But the motivation is kind of, well, it's useful for stuff later on, like calculating length. But the idea is writing everything in terms of something like t. And for part E, it's basically saying, consider your answer again to part A, where we decided that it looks either like a circle or maybe maybe either a circle or an ellipse. And it's just asking you to say, does it look reasonable? So at this point, x should look like r cosine t, y should be equal to y sine t, And z should look like something like blah 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 cosine t plus blah 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 sine t, maybe plus some constant. And the idea here is, does this look reasonable? So what this would be saying is that, okay, the x and the y, as x and y happen, that sort of says, all right, this basically saying just looking at x and just looking like y, the projection of whatever point we have is going to fall onto the circle in the xy plane. But the z component can sort of shift up and down a little bit, right? The z component can sort of like, be maybe up high over here and maybe down low over here. And the idea is it's not asking for anything super rigorous or anything, right? It's just asking, does it seem reasonable? But yeah, I would say yeah, because it's essentially saying the x and y are locked more or less into a circle, but the z can vary up and down a little bit. And presumably it varies in just such a way that you end up getting an ellipse if the plane is tilted, and if the plane is not tilted, it would presumably reduce to just a if the plane was not tilted, I assume it would reduce into just z is equal to c or something like that. Which at that point would just mean it would be a circle, just raised or lowered a bit. Make sense? Any questions? What questions do you have? Folks, am I still talking to people here?
I think you explained it pretty well. I don't have any questions.
Okay, alrighty. Well, that's great. I hope there are no connection issues with the stream. That would suck. Alrighty, so the next parts are just similar variations on the just with new surfaces, right? So next one, it's saying, okay, a paraboloid, z is equal to x squared plus y squared, and a plane 4x minus 2y minus z is equal to minus 25. This one's harder to picture. I'm honestly not 100% confident about this one, but let's just charge in anyways, just full confidence. So the first part asked to draw a picture of the paraboloid intersecting a plane, and I hope you all are reasonably comfortable with what a paraboloid looks like. It essentially looks like a bowl, right? It's kind of a a paraboloid where x squared and y squared have the same coefficient. Namely that they're both equal to 1, is going to have every single cross-section be like a circle. And it's just sort of this bowl that gets wider and wider as it gets taller. So what this is saying is, okay, well, I just said if we drew a plane that's perfectly horizontal and intersect it, we're going to get a circle. So then if you imagine drawing like a slightly different plane that kind of is raised up in an angle or something, I think it would be pretty similar to what we had earlier. Because it's still going to be a loop that sort of goes all the way around. It's just going to be a little bit distorted. Just going to be a little distorted. And at least at a glance, I think it comes out to be an ellipse again. There's maybe some minor chance that it works out to be a perfect circle, but I kind of doubt it. Right? If it was me, I know which one I would probably go with. But okay, then you just also talk about the other possibilities, right? Like what if you intersect it just at a weird, at some edge cases, right? The paraboloid doesn't go down to negative infinity, right? It sort of coalesces to a point down here. So what happens if you intersect the plane z is equal to 0 with this thing? What's the intersection? Can someone say it? Does anybody know? Okay, we're having a bit of a bystander effect here because there are multiple people and no one wants to talk. Shall I just call in names?
I don't know what it would be.
You don't know what it'd be? I mean, I kind of said it earlier, right? Everything just sort of coalesces down to a point, and this point is the only one. Like, how do I put it? If z is equal to 0, right? So 0 is equal to x squared plus y squared. The only possible values of x and y that satisfy this are 0 and 0, which is basically saying that there's only a single point at the height z is equal to 0, just the very bottom of the thing. So the intersection between z is equal to 0 and the entire paraboloid would just be the single point right here. Yeah? And it's almost kind of makes sense as a limit, because like as you have like circles, they get smaller and smaller as you go down, right? And as you get down to like, approaching the thing, they get like sort of in the limit, they just sort of collapse until the circle gets smaller and smaller until it shrinks to just a point. Yeah, what else can we picture? If you did like a perfectly vertical plane, ooh, that's kind of hard to picture. What the hell is that? I think that would look like just a half ramp, right? That would just be a parabola, maybe? Yeah, no, it totally would. It totally would, right? What's up?
No, I was just gonna say I could see that.
Yeah, like literally what we're looking at right here, like doing a perfectly vertical plane is exactly the same thing as doing like a perfectly horizontal plane, right? Namely, like literally the page that we're looking in right now could be considered a plane that we're intersecting the paraboloid with. So just what we get remainder with is literally the shape itself, right? And maybe that's not so surprising that the intersection between a paraboloid and a perfectly vertical plane is what shape that we know from 8th grade algebra. The shape that I drew right here.
The parabola itself.
Exactly, the parabola itself, yes. So what does that look like, right? For example, if I just chose that this was x, then this is y, and this is z, and let me say that let's just look at xz and say, let's let y is equal to 0, right? That's literally the plane of the page right now, y is equal to 0. So then, okay, you lose all the depth, and all that you're left with a parabola is, let's see how this corresponds to the math. This is just saying z is equal to x squared plus y squared. Y is 0, so let's just cancel that out. The equation is just z is equal to x squared. And that's a perfectly genuine parabola that we all know from middle school, right? So you can kind of see how sometimes when things are simple, you get some nice correspondence between math and what you can visualize. And hopefully that makes things a little bit more clear. But yeah, I think that should cover our bases, right? Can you think of any other way to intersect this in a funny way? Right, we did something perfectly horizontal at various heights. I mean, I guess if you did something like down here, the intersection is nothing. It's not very interesting, but I guess you could say it's a null intersection. Right, we talked about the angles of all the flat surfaces. We talked about angles of all the skew surfaces. And we talked about the angles of all the vertical surfaces. And I think that covers it. Yeah, fun exercise. I actually didn't remember to look at the parabola until just now on the spot. But what is this asking us to do afterwards? What is it asking us to do? I think it's basically just suggesting do the same old parametrization. So we're going to solve the second equation for z. Okay. I'm going to use a different equation, right? Just for the sake of keeping things above board. I don't know, 20 or something is equal to maybe like 10. But like just solving it, it becomes like 10x minus 15 equals, or plus 10 over minus 2 is equal to z. So just solve it for whatever equation you all have. And then in the plane, the resulting equation, substitute it into the first equation. Right. So I remember from my notes here. So what's essentially going to happen is once you substitute that into this thing right here, what's going to happen is you essentially get like 10x minus 15y, plus 10 over minus 2 is equal to x squared plus y squared. And the idea here is, okay, let's separate it so that all the constants are on one side and all the x and y terms are on the other. So this looks to me like, okay, I shouldn't have chosen this to be a negative number for reasons that'll become apparent in a second. But let's make this, sorry, if maybe I'll make the z positive plus 2z, okay? So then this negative sign goes away. And the reason why I want to do that is because I'm just sort of rechanging the problem a little bit, is because this turns into a positive number on this side, and this turns into like x squared minus 5x plus y squared minus 7.5y. Sorry, I guess it's plus 7.5y. And the reason I had to choose that constant carefully is because I need this to be positive, because this is the equation of a circle, right? And a circle needs to have a positive number over here. Actually, I haven't totally checked through that this works out yet. But the idea is this isn't quite the equation of a circle we know and love, because really we need this to look like x minus a squared plus y minus b squared, right? So what you're being asked to do is complete the square. Do you all remember how to complete the square? In my estimation, almost 50% of college freshmen, and I've forgotten what that means. But it's just this old technique that we've seen, right? So if x squared minus 5x, this turns into x minus 2.5 squared. And then you have to add in, or I guess you have to subtract out 6.25 squared to sort of make up for that. Or, sorry, you have to subtract out 2.5 squared to make up for that. Does this process ring a bell? Do you all remember completing the square?
Yeah, I remember I forgot it, but then I looked it up.
Yeah. And just to be very clear why we have to subtract this out, this is basically saying this is x squared minus 5x plus 2.5, and then squared. And then we also have to like just subtract out the 2.5 squared so that this and this turn out to be 0. And all we're left with is the original expression x squared minus 5x. So that's the process of completing a square, right? And you just got to go ahead and do this. So this becomes y squared, y minus 3, y plus 3.75 squared. Minus 3.75 squared. Okay, I've chosen awful numbers because these values over here, you know, whatever. No, I think it's fine. I think it's fine. Yeah, so then this, basically the idea is, at this point, you have this minus 2.5 squared and minus 3.75 squared, and you just got to add them to the other side, right? So then this turns into like 5 plus 2.5 squared plus 3.75 squared is equal to x minus 2.5 squared plus y plus 3.75 squared. So then this finally is looking like the equation of a circle, right? And the radius is going to be whatever this abomination is. Well, r squared is going to be this abomination on the left-hand side. I'm pretty sure your problem chooses nicer numbers, but I'm just demonstrating the process, right? Really, I would hope that really you would all know how to do it the moment I said completing the square, but I know that a lot of college students forget, so that's why I bring it up. But, you know, to summarize the cliff notes here is, you take this equation, solve for z, plug that in over here, and then you end up with a bunch of x squared and x terms on the right-hand side and a constant on the left, and you got to complete the square in order to make it look like the equation of a circle. And, okay, find the parametrization for the... Okay, they also ask you to find the center and the radius, right? And the center for this one would just be 2.5. Note that it's a positive 2.5 because this is negative. And this one over here is negative 3.75 because this is positive. Remember that there's kind of a sign difference when you're talking about the center. But yeah, the radius is just this part, right? And okay, then they ask you to find a parametrization of the circle from part B. And the idea here is, whereas before we just were able to do willy-nilly x is equal to r cosine t, now we have to add in the extra term, right? Now we have to add in the 2.5 to kind of represent the displacement. Because the r cosine t and y is equal to r sine t basically just form a circle from wherever the center point is. So you kind of have to like add or subtract the center point out. Does that make sense? Because like drawing this out, this essentially looks like a circle at... so if this is x and this is y, this is at like 2.5 and minus 3.75 with a radius of whatever it is. So if you're representing this with r cosine and r sine, you have to like also take into account the displacement, right? And that's what these terms are. So, okay, using your answers to part C and D, write a vector parametrization. Oh, excuse me. And then D is using the answer from C to write Z in terms of T. Again, things are getting, you know, might be a little bit confusing if you're seeing this for your first time, but just stay confident, right? At this point, we found x of t and y of t. And literally all we have to do is just go back to one of our equations here. If I can find it. Either one, really. Yeah, whatever your equation of the line was, right? And you should be able to just plug that right in. Plug that right in. I think you could also plug it over here if you really wanted to, but I would prefer to avoid the unnecessary squares if possible. Yeah. Maybe I need to do a sanity check here, but I'm pretty sure you can plug it into either one, really. And it should come out to give you something similar. I don't know off the top of my head if it's going to be exactly the same, but it kind of should be, right? Because the entire point was to get the intersection. Anyways, this is a minor aside that I can't seem to work out in my head right now. But the question is just asking you to go back and plug it into one of them, right? And then once you have that for part C, this gives you part D gives you an expression for z of t is equal to, whatever. It's going to involve cosines and sines. And then part E is basically just saying, again, just literally write them all out using some sort of vector notation. That's all there is to it. And then finally, consider your answer to part A. You again have to try to give a wishy-washy answer as to whether or not it's reasonable. And again, I'm going to say, okay, this is going to look like r cosine t and r sine of t, right? And it's going to be plus a term. Let's maybe call it plus x naught and plus y naught. And what this is essentially saying, and the z is going to be a bunch of stuff involving cosines plus whatever stuff involving sines. And again, it's going to be something like, all right, so the sort of foundation here is drawing out a circle in the plane, and then z is sort of like, right, the base is sort of a circle, and then z is sort of like saying, okay, we're going to tilt that up at some points and tilt it down at others. And yeah, I think you could more or less call that a parabola. Call that an ellipse. Unless of course that plane happened to be chosen in just such a way that it was a parabola instead. But I don't think you have to worry about that, because just going back to the visualization, the intersections that are going to turn out to be a parabola were going to be stuff like y is equal to 0, right? Stuff that was perfectly vertical to intersect it and get an ellipse. The difference between something like this, like a plane with some skew to it, is that when you have that skew, it intersects the parabola, and it comes around in a loop. But if you have something like perfectly vertical, like this, the idea is it's going to intersect the parabola at some points, but like it just kind of goes off to infinity. It never sort of like rounds back on itself. You see what I mean? That's the difference between getting an ellipse versus getting a parabola. I guess now that I'm thinking about it, that kind of deeply relates a parabola to an ellipse. I guess an ellipse is sort of like a parabola that just sort of managed to round back on itself. Anyways, feeling good so far? I mean, that's basically what I wanted to cover. I think part 4 is just really more of the same. I mean, we can, if anyone has specific questions on it, we can maybe go over it, but just quickly drawing it out, it's asking about a sphere and a cylinder, right? And the sphere is larger. The sphere has radius, I think, 5. 5, whereas the cylinder only has radius, I think, 3. So, who can tell me what the intersection looks like? This time around, I'm not going to draw it. Someone volunteer and tell me what the intersection looks like. Folks? Any brave volunteers? As these sessions go on, I really got to figure out ways to drive up audience engagement, because I literally have no idea if I'm disconnected when I'm talking. Can someone at least confirm that we're still here?
Yeah, we're still here.
Okay. Well, and what does the intersection look like?
That's a good question. I can't answer that. I
Okay.
don't.
Try to visualize it.
So I'm thinking on the y would be 5, right?
What would be 5? Y?
Yes.
I'm not quite sure what you mean. I'll draw a relevant right triangle to try to give you a hint. But this point over here is definitely a point of intersection, right? And this is at radius 5. And this is going to be at, I guess, sort of distance 3 from the axis, because of the cylinder, right? And the idea is this triangle is basically going to be able to swivel around to each point on the sphere, right? And swivel back around. So what shape does this draw out? You see what I'm doing? You can just imagine like swiveling the triangle around.
Maybe a cone?
Oh, sorry. Only look at the point. Only look at the dots. Don't look The points down here have no intersection. Only look at the points sort of up top here. The dotted lines. What does it form? I mean, I know you all.
Sphere, a circle.
It's just a circle. Yeah, it's just a circle. Can you picture it? Because at sort of a cylinder, really, it's just an infinite number of circles stacked on top of each other, right? And the idea is each of these, you can almost imagine, like, how do I put it? Each of these circles is almost like a mini plane itself. You see what I mean? Like if I asked you the intersection between a plane and a sphere, you would hopefully be able to reasonably quickly tell me that it's a circle, right? But as it turns out that the cylinder is basically the exact same thing. It's just that it only, excuse me. Can you see like the similarity between these two situations? It's like a sphere and a plane intersecting give the circle. So it's like, what if you got rid of the plane and just asked me to intersect that exact same circle with a sphere? Well, you just get that same circle. You see what I'm saying?
Yeah. Sorry.
Yeah. Okay. Good. No, don't apologize for speaking up. Yeah. But okay. So that's what happens up here. So we've talked about one circle. Does this intersect at any other points? Hint. Think about symmetry. We've identified one circle of intersection. Where else would it intersect? Any ideas? Can you see it? So let me tell you this.
Would it okay.
Go ahead. What were you saying?
It would be the same thing going down when it
Yes, exactly. The sphere and the cylinder are both symmetric. I guess I should say it both symmetric across the xy plane, right? So if there's a intersection above, there should also be an intersection below, right? And visually, you can just kind of see exactly the same argument. So yeah, that's exactly I think all there is to it. The rest of the problem, I don't think it's necessarily worth working out because it's just the exact same idea of parametrizing and then solving for z. Really, the process gets quite routine. Yeah. Any other questions?
So it would just be going down the entire thing.
What do you mean going down the entire thing?
You're saying so at the x and y, when it hits the x and y, can you explain it again? I'm sorry.
Yeah, so like the picture isn't super great because it's hard to draw depth in 2D, but like there's an intersection here, right? I hope you're cool with the first circle we talked about.
Yes.
Yeah, like if you can think of the XY plane as like maybe a mirror or something, like the other side of that mirror should have like the exact same thing below. You see what I'm saying?
Got it.
Yeah.
Okay.
Yeah. Okay. So for this problem, I think the only subtlety is that for this one, z is squared, whereas okay, my screen froze, which is kind of annoying. Why does this always happen? Give me a second. Give me just 1 second. Okay, I hope that fixed it. The only subtlety for this one, I think, is that the equation of a sphere is x squared plus y squared plus z squared is equal to 25, or whatever it is, right? The idea is that when you solve for this, unlike the previous problems, this z is squared, which means that at some point, well, okay, it's probably, excuse me, it probably doesn't defy imagination that the fact that we have a cylinder and circles involved means that x should be equal to r cosine t, y is equal to r sine t, right? Use the second equation to write x, y. Oh, actually, wait a minute. Now that I'm thinking about it, maybe they're having you do a different parameterization other than polar coordinates. Yeah, this is a little annoying. But they're asking you to solve for z first and use the second equation to write x and y in terms of t. Okay, no, sorry. Maybe I'm confusing you more than this was worth. But they ask you to start off by solving x squared plus y squared equals 9, right? And subtracting one from the other, you get that z squared is just equal to 16, which lets you know that z is equal to 4. Excuse me, z is equal to 4. And what this is saying is basically that it's saying that these circles are happening at height 4. And lo and behold, this should make perfect sense because a right triangle with one leg 3 and hypotenuse 5 should definitely have height equal to 4, right? So visually, the math and the visual have to correspond, and they do. Good for us. So basically, I'm saying that this height is z is equal to 4, and obviously there would also be a height z is equal to minus 4, because of symmetry, right? So really, I should have said z is equal to plus or minus 4. And I think that should make sense, right? Because when you get a parametrized stuff, when you come up with part, I think this is part D, you're going to get x that looks like, something of cosine t with some radius. And then you're going to get r sine t. And then z should just look like plus or minus this constant or whatever the height is. You see what I'm saying? It's a little bit different where just because you're parameterizing it in terms of t doesn't mean that it has to have t, because it can just be a constant, right? You can kind of see how this corresponds to the image where, okay, x and y cosine t basically describe the circle of radius r. And then the z plus or minus 4 just determines whether or not it gets lifted by 4 or goes down by 4 to describe the two symmetric circles of intersection. So yeah, that's probably all I have to say about that. Any other questions?
No, that makes sense.
Okay, good.